Hey everyone, we're going to start a new chapter today. This is chapter 11, and it's called Direct Products. And we'll start off with a definition. What this is going to be is a process of taking some existing groups and forming a new group, right? And then it's called the direct product. So the direct product of the groups. So we have some collection, say little g1, or sorry, capital G1 up through capital Gn. And so the direct product is the Cartesian product and if you want to get fancy, sometimes it's written this way with a capital pi, I equals 1 to n g sub I. This is often used for Cartesian product, but more often I'm not going to write it this way. I'm just going to write it out G1 cross G2 cross dot 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 cross Gn. All right, so we start off with some groups. We form the Cartesian product, which that's just a set theoretic thing, right? So the direct product as a set is right there, right? It's the collection of all n tuples where the first entry comes from group 1, second entry comes from group 2, and so on. But all I've told you is who it is as a set. Now we need to say who the operation is. And so it's with the operation. And we're going to do things in the obvious way. Let me put it up here. So if I have a G1, comma G2 dot 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 comma Gn times oh, I should have used little a's. Let me use little a's and b's here. Yeah, so an element, let's call it little a1 dot 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 an times b1 dot 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 bn equals, and so in the first entry we'll have a1 b1. In the second entry, we'll have A2, B2, and then we'll get down to AN, BN. Okay, so we've got this thing called the direct product. As a set, it's the Cartesian product. We've given it an operation. We want to quickly actually verify that this is a group. But before I do that, let me point out what we mean here. When I write A1 times B1, what I mean is use the operation in capital G1 to create this element right here, A1 times B1. So this is the operation in G1. And then right there, when I write down A2 times B2, this is happening inside G2, so that's the operation in G2, and you go all the way down the line. When you get to AN times BN, that is the operation in G sub n, right? So remember, these are different groups. They might have completely unrelated operations. A1 may have absolutely nothing to do with A sub n, right? Because they live in totally different groups. Okay, so let's check that it's a group. So we show that, let's call it capital G. So capital G is the Cartesian product of the GI. So we show that G is a group. So let's see, we need associativity. And associativity is going to come straight from the associativity in each of the component groups, right? So associativity in G follows from associativity in each G sub I, capital G sub I. What do I mean? I mean, maybe I'm being a little bit lazy there, right? If I take 3 n tuples, what will the entries look like? So I would have an A1, I'm just going to kind of slop this out real quick. A1 dot 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 AN times B1 dot 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 Bn times C1 dot 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 Cn. Now, if you multiply this together, what you're going to get written this way is going to be, in the first entry, a little A1, B1, C1, all the way down to AN, BN times Cn. Right, so that's what it would look like, and then you use the fact that G1 has associativity, so move the parentheses here. There'll be some parentheses in G2, or use associativity to slide the parentheses in the second entry. All the way down, slide the parentheses over, and then unravel things. So associativity comes directly from the fact that we have associativity in each of the capital GIs. We need, what else do we need? We need an identity. Who should the identity be? Well, let's write it like this. The identity is equal to E1 up through E sub n, where E sub I is the identity in capital G sub I. And then the last thing we need is inverses. So who will the inverse of some random element A1 up through AN? Well, okay, think about the operation and think about what you would need to put. It will be A1 inverse, comma, A2 inverse, comma, dot, 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 AN inverse. All right, so easy to check that this construction actually gives us a group. I want a few remarks before I actually start doing examples. So, so I'll say note, some authors use this symbol, a plus with a circle around it, the circle plus symbol, in place of X. Right, and then they'll call this, and call the direct product, instead of saying direct product, they call it the direct sum. So it just makes life confusing because different authors use different notation to indicate exactly the same object, the same group. So you just want to be savvy enough to go back and forth when you see direct product or direct sum, think the same exact thing. And then this is most common. So this is most common when everything's abelian. So when all GIs are abelian. What else? Oh, right. And in this case, when they talk about the direct sum, then the notation for the operation is not going to be juxtaposition of n tuples. It's going to be sum of n tuples. Right? So in this case, you're right. A1 dot 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 AN plus B1 dot 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 BN. The second thing, so this was really, I guess, my first note. I should have labeled that note 1. And then the second note, what we defined as a direct product. So the direct product defined here is what's known as the external direct product. So this is the external direct product, to be distinguished from what's called the internal direct product, which will come up later. And so I don't want to make a big deal about this yet, but we will have another thing called the direct product, and it's the internal direct product, and then we'll see what the difference is. So just be aware that there are times when I want to be specific, and I'll say, by the way, we're talking about the external direct product. So some examples. How about this one? Z3 cross S4. Right, there's an example. I take two groups, I form a new group. Now, what would a typical element then look like? It would look like an integer 0, 1, or 2, comma, sigma, where sigma is some permutation in S4. Right, so there's an example of a direct product. So more examples, Z cross Z, which will be used interchangeably, Z sum Z. Right? Both of these mean exactly the same thing. The objects are things of the form A comma B. And then it does make more sense to think of it as the operation being plus, because when you actually combine this, what you get is A plus C comma B plus D, because the operation in both entries is addition. So just be aware, I tend to go back and forth between these two things. It means the same thing, set-wise. It's just the set of ordered tuples. And then the operation is whatever operations you get from the component groups. In this case, because we have Z's in both cases, it's addition in both cases. But in your book just uses the X symbol, the Cartesian product symbol, or the Cartesian product symbol. So your book does not use that symbol, but still, you'll put a plus in between those things because the operation is addition. How about this one? Z2 cross Z3. Okay, so now the elements are going to be ordered tuples A comma B, where the first element comes from Z2, the second element comes from Z3. So for example, how about this? 1, 1 plus 1, 1. What do we get here? Well, what we'll get is 0, comma 2. Why is that? Because when you add the first entries, you get 1 plus 1 mod 2, which is 0, and then you get 1 plus 1 mod 3, which is still 2. All right, so there's some examples. Actually, I want to take a closer look at this group, Z2 cross Z3. So, a closer look at Z2 cross Z3. Well, so first, let's just write down who this is as a set. Who are the elements? Well, there's 0, 0, that's the identity. And then there's 1, 0, and 1, 1, and 1, 2. There's 6 elements here. So who else is there? There is 0, 1, and 0, 2. All right, I got all 6. Now, I want to look at the orders of these elements here. So, of course, the order of 0, 0, all right, that's the identity. The order is just 1. Now, let's look at the subgroups generated by various elements. So if I look at the subgroup generated by 1, 0, let's see what I'll get. I'll have the identity, of course, and then I'll have 1, 0. But if you add 1, 0 to itself, right, you get 0, 0. All right, so that's the entire group there. Let's look at 0, 1 also. And so you'll have the identity, and then you'll have 0, 1, and then you'll have 0, 2. And if you add it to itself one more time, you're going to get 0, 0. So there's 3 elements in that group. Right, so what am I getting at? The order of the element 1, 0 is 2, and the order of 0, 1 is 3. But now, if you look at the subgroup generated by 1, 1. Okay, so it's definitely going to have 0, 0 in it. And what I'd like to do is just start adding 1, 1 to itself. So of course there's 1, 1. Add it to itself, you get 0, 2. Add it to itself again, so 1, 1 plus 0, 2 is 1, 0. Do that again, 1, 1 plus 1, 0 is 0, 1. Do it again, so 1, 1 plus 0, 1 is 1, 2. And then if you add it to itself again, 1, 1 plus 1, 2 is going to be 0, 0. Right? So what did I do? I start off with 1, 1 and start adding it to itself. And we find that you can do that when you do it the 6th time you get back to the identity. And so the order of 1, 1 is equal to 6. In particular, the subgroup generated by 1, 1 is equal to all of Z2 cross Z3. This group is cyclic. Z2 cross Z3 is cyclic. And we know that there's exactly one, up to isomorphism, there's exactly one cyclic group for each order, right? And so our conclusion here, right? Every cyclic group of order 6 must be isomorphic to Z6. So in particular, Z2 cross Z3 is isomorphic to Z6. As another example, let's look at Z2 cross Z2. And so I want to just run through the orders. Of course, the identity has order 1, but if we look at the other elements, so let's see, the subgroup generated by 1, 0. That's equal to, well, it's got the identity, and it's got 1, 0. But if you add 1, 0 to itself, you get the identity. And then let's look at 0, 1. Same thing happens. You've got the identity and the element itself. Right? But this element has order 2 also. And then 1, 1, that's the other non-trivial element. I should have written this out, right? There's 4 elements. Sorry, I did this out of order. That should be 0, 0, 1, 0, 1, 0, 1, and 1, 1. Those are the elements in Z2 cross Z2. And so now the subgroup generated by 1, 1, it's got the identity, it's got 1, 1, and now if you add 1, 1 to itself, you get the identity back, so this element has order 2 also. So what I did, I ran through all non-trivial elements of Z2 cross Z2, looked at the subgroup generated by them, and we never got Z2 cross Z2 back. In other words, Z2 cross Z2 is not cyclic. Now, we studied groups of order 4 and found that there's exactly 2 of them. And we were able to sort of characterize them like this. There was Z4, and then there was V. And V is defined by its Cayley table. But now, knowing that Z2 cross Z2 is a non-cyclic group of order 4, that means that the Klein 4 group has to be isomorphic to Z2 cross Z2. And that's kind of nice, because up until this point, when we talked about the Klein 4 group, we had to think of it in terms of its Cayley table, which is kind of a pain. Now we have a nice way to think of the Klein 4 group. It is Z2 cross Z2. And so typically when we talk about the subgroups, or the groups of order 4, it's Z4, the cyclic one, and Z2 cross Z2, the Klein 4 group, which is the non-cyclic one. So a couple of sort of, I don't know, obvious questions, say natural questions. So 2 natural questions. All right, we formed this thing called the direct product. The first of the sort of obvious questions, right? We want to, once we've created this group, right? Out of existing groups, we would like to understand the nature of this direct product, and its nature should somehow have something to do with the nature of each of the individual groups that make up that direct product. And so one question so would go like this. So if G is the direct product, or is a direct product, of groups, and little g is in capital G, how do you find the order of that element? So how do I want to say this? Let's just say it like this. So what is the order of little g? Now remember, little g, because it's in a direct product, little g is going to look like some direct, or some tuple, g1, g2, up to gn. Right? And so the question would become then, what's the order of an n tuple like this living in a direct product? Right, so there's a first sort of natural question you might want to ask yourself. And a second question, and that's kind of related to this thing we did here, where we took the direct product Z2 cross Z3 and we found that it was cyclic. Then we did Z2 cross Z2 and found that it was not cyclic. So there's a general question then, if you have direct products, when is the resulting group cyclic? So let's say when is a direct product cyclic? And these two questions are related. It's going to be cyclic if there's an element in G whose order is equal to the size, the cardinality of that direct product. All right, so those are a couple of the questions that we want to address. And how much time we got? Yeah, I think I'll just do this theorem and then we'll call it quits. So this is theorem 11.1. So if G and H are groups, and let's say little g is in capital G, and little h is an element of capital H, have finite order, right? So G and H themselves capital G and capital H may not have finite order, but we're taking elements of finite order within those groups. Then we can look in the Cartesian product, and so the question is, okay, what is the order of G comma H? And it turns out that it's the least common multiple of the order of G and the order of H. Maybe not too surprising. So here we're computing the order within the direct product G cross H. So for the proof, I want to write this out. So let's write S equal to the order of GH, and T is going to be the least common multiple of the individual orders. Right, so our job is to show that little s equals little t. Now, right, so we can say then, if I look at G comma H to the t, G comma H to the t, let's see what that would mean. It would mean multiply G times, or G comma H times G comma H, etc. This is equal to G to the t times H to the t. And so now what do we know? Well, let's see. T is a multiple of the order of G, which means that G raised to the T has to be the identity. Same thing, T is a multiple of the order of H, which means that H to the T has to be the identity. This is, right, okay, so this is equal to E sub, let me write it as E sub G comma E sub H. Now, what do we know? Anytime, if we have some power, we raise an element to that power and we get the identity, then we know that the order of the element has to divide that power. So it follows. So it follows that S divides T. That goes back to our lemma 6.5b. Right? This exponent always has to divide the order of the group. And so what does that tell us then? It tells us that S is less than or equal to T. So thus S is less than or equal to T. Okay, so now let's say no. If I look at E sub, what am I doing here? E sub G and H, yeah. E sub G comma E sub H. Oh, right. This is equal to, of course, G to the S. Well, let's write this out better. G comma H to the S, right? Because S is the order of G comma H. This is equal to G to the S comma H to the S. And so let's see, since G to the S is equal to EG, right, so since G raised to the S power is equal to E to the G, what does that tell us about S? It means that S has to be a multiple of the order of G, right? So since G to the S is equal to E sub G, we have S is a multiple of the order of little g. And the same thing, we've got H sub S equal to E sub H. So similarly, S is a multiple of the order of little h. Now, what do we know? T is the least common multiple. All right, so since T is the least common multiple of the order of G and, say it like this, least common multiple of order of G and order of H, what does that tell us about the relationship between S and T? It tells us, because T is the least common multiple, T has to be less than or equal to S. We can say, we conclude that T is less than or equal to S. So now we have S less than or equal to T, T less than or equal to S. That tells us that they're equal, so therefore S equals T. That's what we need. And now, what we did is we proved this result in the setting where we're doing G cross H, where there's two component groups. But more generally, so this will be just sort of a quick corollary. So corollary 11.2, if G1 up through G sub n are groups. And we take a bunch of gi's of finite order and G sub I in capital G sub I has finite order. Then the order of the element G1 up through G sub n is going to be the least common multiple of the orders individually, so G1 up through order Gn. And what's the proof? Well, it's induction, where our theorem is the base case. So proof. Induction, so if you like, you can write up a proof, but it'd be just a straightforward induction proof. So let me see. Let me just do. Let me do a couple of examples here. So let's say in Z3 cross S4, let X be the element, how about 1, 1, 2, 4. Well, then the order of X is going to be the least common multiple of the order of 1 in Z3 and the order of 1, 2, 4 in S4. So then you say, okay, what's the order of 1 within Z3? Well, it's the generator, right? It has order 3. And the order of 1, 2, 4 is also equal to 3. And so, right, this element X has order 3 in Z3 cross Z4. And let's say in Z25 cross Z100. In Z25 cross Z100, let's look at, who do I want to look at? Oh, how about the order of 5, 5? Well, the order of 5 let's write this out, LCM of, the order of 5 in Z25 is 5. The order of 5 in Z100, 5 plus 5 plus 5, add it to itself, you get 20 times, or 20. And so the order is 5. No, it's not. It's 20. The order of, let's look at the order of 10, 50. That's going to be the least common multiple of the individual orders. What's the order of 10 in Z25? 10 plus 10 is 20, plus 10 is 30, 40, 50. The order of 10 is 5. And the order of 50 is, in Z100, is 2. And so this element has order 10. All right, that's a good place to stop for today. So we will see you next time, okay? Bye.